In section 2.1, we're going to be discussing how do we read and recognize different kinds of statements which we can assign a true or false value to. We call these propositions. A proposition is a statement in which we can assign a truth value of true or false. So these examples I have down here to start out with are propositions. We can either say true or false to each of them. The first one you can see here is verifiably false. We can say false to that. Julius Caesar was president of the United States. So pretty clear to see what that one is. This one over here says 2 plus 2 is equal to 4. We can say to that it's either true or false. In this case it would be true. However, something like 2 plus 3 equals 7 is something we can say that is false. Now, some propositions are made up of connective words like and, such as the statement, the number 4 is positive and the number 3 is negative. So we kind of look at each of these parts that are being connected with and. We can assign a truth value to each of those. For instance, the number 4 is positive would be considered true, but the number 3 is negative, well, that's false. So overall, the proposition together would be considered false. Since we see that we have one true and false, then we would only expect this proposition to be true when both statements connected by and are true. So this next one down here says if a set has n elements, then it has 2 to the n subsets. We haven't actually talked about if this is true or not, but if then is a common connective way that we put together propositions. If something, then something. This proposition is actually true in this case, and we can verify this one later. And then the next one down says every even integer greater than 2 is the sum of 2 prime numbers. This is a proposition, but whether or not it's true is actually still an open question. So while it can be assigned a true-false value to the proposition, it's still unknown which one of the two it is. Now the next two down below, I want to highlight for the words for all and for some. And the first one says x plus y equals y plus x for all x, y in the real number set. This is technically true, and it's only true because it applies to all x and y in the real numbers. If it failed to be true for all, then the whole proposition would not be true anymore, it would be false. You can contrast this to a proposition that says for some. If it's for some, then you don't have to verify for all. You don't have to think about everything, just at least one example that works for a smaller subset. It doesn't go for all necessarily. So this one is technically true as well. Whether or not it's true for all is another type of proposition altogether. But as long as we can say for some that it works, then the whole proposition is true. The next one below says 3 is an even integer or 7 is a prime number. There's another one I wanted to highlight for the word or in the middle. We have two parts here. We can say true, false to either one of those. So 3 is an even integer. Well, that's false. 7 is a prime, though. Well, that is true. So since this is an or situation, the whole proposition technically is true because you don't have to have both at the same time like you would if you said and this. Either one is sufficient to be true to make the whole proposition true. And then the last one's kind of a nonsense statement. If the world is flat, then 2 plus 2 equals 4. Another if-then situation, but it is still the form of a proposition that can be assigned a true-false value to. We'll come back soon to talk a little more about the if-then situations and kind of the odd characteristics they have when we start assigning true-false values to them. Now, to highlight situations where we do not have propositions, Here's example 2. We want to see why some of these would not be considered propositions or would be considered just ambiguous. The first two, why is math important, go directly to jail, those two are not propositions because we cannot assign a true-false value to those. One is a question in the form of a question, and the other is just a command. So those are not propositions because it doesn't make sense to say that one is true or false, The next three can be considered propositions, but only if we remove some of the ambiguities. The first one that says x minus y equals y minus x, it's ambiguous what x and y are. As long as we are not specifying what they are, this really cannot be assigned a true-false value. It's not a proposition. The next one is also ambiguous because it doesn't state, are we dealing with all teachers or some teachers? So until we clear up that ambiguity, it's really hard to say true or false in general. And then the last one that says math is fun, again, same kind of idea. We don't know, is all math or is some math fun? We need to specify, are we talking about all of it or some of it if we're going to be thinking about a true-false value for that type of proposition. And the last one, it says a squared equals 0 implies a equals 0 for all a. Seems to be constructed like a proposition, but we don't know what a is. Is it a number? Is it a set? What kind of number? Until we specify that, there's no use in trying to consider it a proposition that we can assign a true-false value to. So as we go about discussing compound propositions and some of the connective words used in there, we're going to start using some symbols to represent them. And so the most common ones we're going to use is we're going to have a symbol for not or negation, not this or not that. We'll use this little symbol. And then sort of an upside down V symbol is going to stand for and. Kind of this V symbol will stand for or. This right arrow is going to stand for implies or the implication. And then this double arrow is going to stand for if and only if, sometimes called a biconditional. For the implication, oftentimes the way the propositions are constructed is the if-then situation. So if we see if-then, then we can use that little right arrow to stand for if this, then this, or in other words, this implies something else. So let's look at a few examples here where we're going to take these propositions and write them using the connective symbols we have. Now, in order to do this, we oftentimes take part of the proposition and let a letter stand in for that thing. So for this first one, I'm going to let the letter P stand in for the part of the proposition that says the number 4 is positive. And I'm going to let the letter Q stand in for the part that says the number 3 is negative. And then I'm going to use my connective symbol for AND from up above to put together these two things. And so this would go together in logical connective form as P and Q would be how we write that, with the P and the Q standing in for those parts of the proposition. Now down here, this next one, I'm going to let the first part of this, let's let R stand in for that part, and let's let S stand in for the next part. So R is going to stand for the part that says the world is flat. And S is going to stand in for the 2 plus 2 equals 4. And we'll write this with connectives as R implies S, because our proposition is if, then, it's the same thing as saying at the R first part implies the second part. So we'll use that little right arrow to stand in for our proposition structure, with R standing for the first part and then implies S. Now down this one here down here below has OR in it. So the OR symbol was that V. And so let's let some letters stand in for the two parts that are being connected by OR. Let's use the letter P here again to stand in for the first part that says 3 is an even integer. And let's let the letter Q be there for 7 is a prime. So I'll write this with the OR symbol as P or Q. So these are all kind of shorthand ways for showing the structure of our proposition, where each letter is standing in for the different parts that are being put together by the different logical connectives. Okay, now let's take some statements which are put together with letters and logical symbols and put them back together into words. So here we have P stands for I am driving, Q stands for the store is open, and R stands for I have groceries. In this next example here, we're going to take some letters which are already set up with what they refer to, and then take the logical statement that we have here with the logical symbols and rewrite it back in words. This first one has P and R implies Q. So let's read off what P stands for. P stands for I am driving, and then the logical symbol is for and then P and R, so that would be and I have groceries. And then the logical connective next is implies, so we'll just go ahead and use implies Q, which means the store is open. So that's how we read off the symbolism that we have here back into words. So an alternative way we could write this, rather than saying implies, we could say if I am driving and I have groceries, then the store is open. So we could write it as an if then rather than implies. So here's one that has two implications. So starting with P, it says, start off with I am driving, and then I'll go ahead and write that as implies R, which stands for I have groceries. And then the next one is implies the last one, which is Q, and Q stands for the store is open. Okay, now this last one's a little bit longer and has some different of these symbols in here. The first one is that little symbol which stands for not or negation. So it says not R. So when I write this out, I'll do the not version of R, which stands for I do not have groceries. And then the double arrow stands for if and only if. So I do not have groceries if and only if, not P, which would be I am not driving. And then we have the logical symbol for or not Q, which stands for the store is not open. So that's how we would read off this. Not R, if and only if, not P, or not Q. So there are a particular kinds of propositions which can follow from a logical implication. For a proposition of the form P implies Q, we have something called the converse and the contrapositive. The converse is basically the reverse implication. So instead of P implies Q, it would go Q implies P. The contrapositive is also a reverse, but also with the not or negation included. Not Q implies not P is the contrapositive. So let's consider this sentence. If it is raining, then there are clouds in the sky. We're going to let P be it is raining, Q, there are clouds in the sky, and write the converse and the contrapositive. So an alternative way of reading this statement, since it's an if-then, is to say that it is raining implies there are clouds in the sky. With letters and our logic symbols, it is raining again is the P, and there are clouds in the sky is the Q, and implies is the arrow to the right. So we'd write this as P implies Q. The converse is always the other way around, would be Q implies P. So we would read that out as there are clouds in the sky implies it is raining. Or another way of saying it is if there are clouds in the sky, then it is raining. So it's the other way around from the original statement with the if-then, rather than if it is raining coming first, the if there are clouds in the sky comes first, then it is raining comes second. The contrapositive is like the converse, but with the not or negation as part of each of the letters here. So it would be not Q implies not P. And so that would be read off as if there are not clouds in the sky, then it is not raining. Okay, now to round us off here, we want to talk about two last symbols. One that means for all, and one that means there exists. This thing that looks like an upside down A, that stands for all. And this thing that's a backwards E means there exists. So here's a situation where we'll find a counterexample to the statement 2 to the n plus 5 to the n is prime for all n greater than 1. So that's what that symbol is going to stand for here. Okay, and so in order to consider something that goes counter to what this says, we just have to find one thing that does not agree with this proposition. So basically find an n for which 2 to the n plus 5 to the n is not prime. Because to do that will go against the thing that says for all. So if it's not true for all, if there's one that exists that goes against the proposition, then we know the proposition is false, and we find a counterexample to it. So let's just try some numbers. Let's try an easy one. Let's say 2 to the first power plus 5 to the first power. Well, that is 7, and that's still prime. So for that number, the proposition is still holding true so far. If we go 2 to the second plus 5 to the second, that would be 29, and that's still prime. So we're just going to have to keep going and see if we can't find a number for n that causes it to be not prime. Now I had to go a ways to find one that works, but I went all the way to 2 to the fifth plus 5 to the fifth. And I found that is equal to 3,157. And this is actually not prime since it's divisible by 7. So this is a counterexample. So we'll say here the counterexample is for n is equal to 5, 2 to the n plus 5 to the n is not